Jnanam paramam dheyam. Knowledge is supreme.
Today the theme is to look at, just like in classical mechanics you have active viewpoint and passive viewpoint, right? What is active viewpoint and passive viewpoint? Coordinate axis is kept fixed and you look at operations on the vectors, or you try to look at the operations of the coordinate axis. So those are the active and passive. I'm sure you have all seen this, right? So similarly, even in quantum mechanics, you can have two pictures. One is called as a Schrodinger picture, the other one is called as a Heisenberg picture. Okay, so we will try to, the physics is the same whether you work in Schrodinger picture or Heisenberg picture, but you should not do half of it in Heisenberg, half of it, then you will not get. The same thing with the active and passive viewpoints, right? So we will get to this. Before I get on to this, I thought I should complete what we said in the last lecture about incompatible observables, okay, not observers. So incompatible observables are two linear operators, Hermitian operators, whose commutator bracket will be 0 or non-zero? Non-zero, right? So this is what we saw, that in that specific case you wanted to show that the standard deviation of operator A multiplied by standard deviation of operator B, this should be greater than or equal to expectation value of the commutator bracket. If they are compatible, then it will be 0. So you can simultaneously measure the two compatible observables. There is no disturbance, there is no uncertainty. Only when there are incompatible, then you have this problem that the two standard deviations or two uncertainties, the product is having a bound which is determined by the commutator bracket. And this is the question, you need to prove this. Okay, so let me just briefly recap on the slide the solution for others who have not tried it, but you can go back and rework things. I have not put in all the steps, but essential steps are put in here, okay. So first you try to write a small little a to be the operator A minus the expectation value of the A operator. So this is basically taking you deviation from the mean value. Similarly, little b in the same way. What happens to the commutator bracket of A with B? A with B commutator bracket, what will happen to it? It will be same as little a with little b. Why? Expectation value is some kind of a number, so it doesn't really play a role. Okay, so expectation value is a number, so you can try to check that little a little b commutator is same as the observable operator A commutator with B. Then you can also use this fact that if you take the matrix element of the little a b operator between some arbitrary state psi, you interchange that, that's nothing but the commutator bracket evaluated as an expectation value, right? And you can, this step you can verify, okay, you can try to write A with psi as some phi, B with psi as some chi, and then this will be the star of it. So if you take an inner product of two states minus the star of the inner product of those two states, the difference will always be proportional to the imaginary value. Okay. Will you try this? Just check it out. Take B with psi as some new state, A with psi as some other state, and you can try and show that this, use the inner product property. What is the inner product property? They are Hermitian operators. They are observables. Okay. So use these two properties and you can show that psi with commutator AB is twice I imaginary part of. Okay. I'll leave it to you to check this. Okay. And now you can add further. Imaginary part is always less than the magnitude or the, so you can take that modulus and then use your Schwarz inequality. What is Schwarz inequality? The dot product if you take, then you can show that that modulus squared is less than the norms of the individual states. Is that right? So now you can plug back this into this, and this A psi with A psi is nothing but delta A squared. This also you can check. So once I put this in, so this is delta A squared, this is delta B squared, and you go back here to the step and you can show that, and the commutator of AB is commutator of capital A capital. Hence you can prove delta A delta B. Okay, so I've just given you the heuristic steps. You go back and fill in the gaps and you'll be able to prove this. Okay. So I don't think there is a mistake in this half factor, this overall two factor, because this imaginary part is what you are going to say and then you have to put in the 2i to get going. Any questions? So the theme of this equation is to show that if you have incompatible observables, there will be uncertainty in precisely measuring both the observables simultaneously, because the commutator bracket is non-zero. So that's why the commutator bracket of x with p equal to, it's not equal to 0, it is non-zero. That's why you have uncertainty. If you try to measure precisely the position of the particle, you lose information about the momentum or equivalently the wavelength of the wave, and vice versa. So any two operators whose commutator is not 0, then there will be uncertainty in the measurement. You cannot simultaneously measure both of them precisely. So that's the verbal way of saying the mathematical equation which I have written. So this 2i should be removed here. This imaginary part is less than or equal to this, and then you substitute it here and then you will start seeing. So I was just telling you that there are two viewpoints, but the physics has to remain the same. One of the convenient viewpoint which we follow in quantum mechanics is the Schrodinger picture. Okay. So what is Schrodinger picture? This I have already said in the beginning. The state vector evolves in time. Okay. So the way we try to write, if you remember psi of t, we wrote a unitary operator t comma t naught on psi of t naught. So we took the state vectors to evolve in time, but when we want to find expectation value of x for a system prepared in the state psi, we try to write this as psi of t x psi of t. So the x operator does not have any explicit time dependence. Like you could have some operator like a operator as x cube plus t times xp squared, could have some operators like this. This is Hermitian. So this has a explicit time dependence. We are not looking at such operators. When I say x X does not have explicit time dependence. P, angular momentum L, which is R cross P, no explicit time dependence. Okay. But because the state vectors are evolving in time, you could do time derivative of the expectation value of X, which in principle could be a function of time. Right? So those are the kinds of things which we do in Schrodinger picture, where we look at these operators which are independent of, there is no time dependence there. The time dependence is put on the state. So the time dependence shows up on the state vector, but the operator is independent of time. Okay, and we are looking at simple operators which don't have any explicit time dependence, or this kind of operators. This is also an allowed operator, but this has an explicit time dependence. We look at operators of this type which don't have an explicit time. State vectors evolve in time, but operators X and P do not evolve with time. As operators they don't. As matrix elements of those operators, that matrix element itself could be having an evolution in time due to the state. So take such operators which corresponds to observables, if there is no explicit time dependence. We could take, this could be a position operator, or this could be a momentum operator or angular momentum operator. State vectors, you could have matrix elements between two different state vectors at the same time. Equivalently, you can use the Schrodinger evolution equation, which is the unitary operator acting on the initial state at initial time t0. Similarly, on the bra vector, it's going to be the U dagger. So this matrix element on the left hand side explicitly can be written as the matrix element between the initial states, take the initial time to be t0, and with this unitary operator on both sides, sandwiching the A operator. What is this unitary operator? We have done this. This is e to the minus I h t minus t0 over h cross. So U dagger will be the inverse of it. Okay. So the matrix element alpha of t, you can write alpha comma t or alpha of t, both are equivalent, and then some observable which has no explicit time dependence, beta of t, you can write this as alpha of t0, U dagger t comma t0, A operator U of t comma t0, B of beta of t. This is kind of ringing some bell. Something it conveys, this equation. What does it convey? You can try to freeze the state, change the operator, and make sure that the matrix element, whether I work with the state evolved or the operator evolved with the state fixed, is the same. Okay. So this is what it tells. Either you evolve the state and evaluate the matrix element, or you fix the state and modify, put this to be time dependent. This is what I was trying to say, that there are two viewpoints. One was the Schrodinger picture, which was this left hand side, which you have done many times. But can we try to freeze the states to be an initial state and put whatever is the modification on the operator? So that is what is being done. So this kind of gives us an indication that you can equivalently view the above equation in a different picture. That different picture is called as a Heisenberg picture. Okay. What is this picture? Now I have already spelled it out. It's the converse. Make the state vector to be frozen to some specific time t naught. Don't allow it to evolve in time. But make all your linear operators corresponding to observables, which are Hermitian operators, to evolve in time. But what is the form? It is not arbitrary. It is dictated by the matrix element which we saw in the earlier transparency. So what is that form? The form is suggested by looking at this equation that there is a time evolution of operator A of t, which should be the A operator at a specific time t equal to t naught, and you do the time evolution in this way. Okay. So this is very important, that in the Heisenberg picture, we take the states to be frozen at t naught, and we take all your operators at t naught and then multiply u dagger, pre-multiply u dagger and post-multiply u to write the time dependent operator. To be very precise, I should put a subscript h here. Okay. So let me write it here. So Schrodinger picture, Heisenberg picture, so you will have psi of t, okay, and you can, if you want, you can put an s here just to remember that it is a Schrodinger state. Equivalently, I could write here psi h without putting any time dependence. That's nothing but psi s at t0. You freeze the state in the Heisenberg picture that it is fixed at t naught. So any operator here which I write as, ah of t will be u dagger t comma t naught, as u of t comma t. This as can also be treated to be equal to operator is frozen here. There is no time evolution of the operator here, but there is a state evolution of the states here in the Schrodinger picture. Equivalently, in the Heisenberg picture, states don't evolve in time, but operators evolve in time. What happens to the Hamiltonian? Hs here and Hh here, are they different or are they same? Why? This involves exponential of the Hamiltonian operator. They will commute. U dagger u is identity, right? U dagger u is identity. U dagger h u is also But U dagger, some other operator A, this is not equal to A in general. So because of this property, U dagger HU equal to, you can show that this is same as, you can write formally as H. Hamiltonian is same in both the pictures, but other operators in Schrodinger picture don't evolve in time, whereas they evolve in time dictated by the time evolution operator. And this is done in such a way that the matrix element evaluated in the Schrodinger picture is going to be same as matrix element evaluated in the Heisenberg picture. Yeah, so this is just to summarize here. Use subscript S to denote Schrodinger, H to denote Heisenberg. So the operator in the Schrodinger picture is A subscript S, and you can write the Heisenberg operator, which is time dependent, as the unitary evolution. The dagger operation from T to T naught or T naught to T can be equivalently written as without the dagger, but interchanging the initial and the final time, right? Instead of going from T naught to T, you can go from T to T naught, which is an inverse step. These are things which you should play around with the unitary operators. You can write U of T comma T naught. You can also write this as U dagger of T naught comma T, right? Both are same. The ones which I have written here is for the operators. Similarly, the states, you can write the Heisenberg state to be frozen at T naught, which is the Schrodinger state. Equivalently write this in terms of alpha S of T, and you can use this U unitary operator from T naught to T to relate any state at time T in the Schrodinger picture to the Heisenberg frozen state. So play around with these unitary operators. U dagger T comma T naught is nothing but U T naught comma T. As I said, alpha of T, the state evolution is what I call it as a Schrodinger picture states, and you can relate the Heisenberg picture states, which is independent of time evolution. This is U dagger, there will be a U dagger is identity, so you will get alpha H to be alpha of T naught. These are all various ways in which you can write the same state. Is this clear? So this is what is always insisted, whether you work in viewpoints which are passive or active, the physics cannot change. So the matrix elements are the ones which contains the physics. So the matrix elements in both the pictures should remain the same. So either you work with Heisenberg picture, where we evolve the operators as functions of time, but you don't evolve the states and do the calculations. Equivalently, you could evolve the states and keep the operators independent of time and do the matrix elements there. Both will be the same. Sometimes it becomes convenient to choose which picture will be much more convenient, okay. So just like if when we did this earlier basis, I was trying to say that choose a basis where it becomes the eigenvalue basis for some operators. Similarly here, sometimes the convenience will be work in Heisenberg picture will be convenient. Sometimes Schrodinger picture will be convenient, and you can decide depending on the given quantum mechanics problem, okay. But both are equivalent. Both are equivalent. You can work either in Schrodinger picture or you can work in Heisenberg picture. So both are equivalent in the sense that if you try to matrix element of a operator in the Schrodinger picture which is time independent, where the states are time evolving, this is same as freezing the states and working the time evolution of the operators, which we call it as a Heisenberg operator.